Hi everyone, welcome to another video for research design and analysis. This is our third video on our series of dealing with models with repeated measures. In the previous video, we talked about a conceptual introduction to the repeated measures ANOVA, and we explained how it's, conceptually exactly like factorial ANOVAs that we've done in the past. The only difference is that now we have to account for the fact that we have multiple observations per person. In this video, we're going to be talking in detail about how do we actually account for that in the analysis of variance table. So this one is a little bit stickier when it comes to the actual calculations and what's going into each of those different cells of the tables. But feel free to pause it, refer back to the previous video. And remember, conceptually, it's exactly the same as what we've done before. The only difference is that now we have to remove the variability due to what person you are, and then we can calculate our treatment effects more accurately. So let's consider a hypothetical experiment where we were looking at anxiety ratings from participants when they either had an experimenter absent or an experimenter present in the room with them at the same time during some kind of taxing test that we're giving them. So in general, these anxiety ratings are above average, and we want to see, was the anxiety lower when the experimenter was absent compared to when it was present. We could analyze this, again, using some sort of t-test or analysis of variance, right? But the important thing to recognize is that here we have crossed conditions with participants, and each participant is being assessed at two different repeated measures, right? There's two different time points. This isn't a group who is randomly assigned to have an experimenter absent, and it's not a group who is randomly assigned to have an experimenter present. It's the same person in both conditions, and therefore we need to account for that person's average when we do the calculation of the difference between these two conditions. So I'm going to use y sub hi, where h equals the condition and I equals the participant. But otherwise, I'll be showing you how we can use the information presented here in order to ultimately fill in the analysis of variance table that we would get if we did a repeated measures ANOVA in a stats program like Jamovi or R or SPSS over here. So this is the completed analysis of variance table, but on the next slides, we're going to step through each of these calculations and how we get them based on the data that we have available. So first, let's calculate our sum of squares total, because that's a relatively easy one to do. The sum of squares total is just going to be each observation for each person in each condition relative to the grand mean. So I would take each of these scores, subtract off the grand mean, square them, add them all together. In this case, that happens to be a sum of squared errors of 23. And the degrees of freedom here are going to be 15 because we have 16 total observations minus the one parameter that we need to estimate. So n minus 1 is 15. We have 15 degrees of freedom here. Next, we can fill in the variability within subjects, right? How much variability within subjects is there? And remember, our manipulation occurs within subjects, so we want to explain variability within subjects in this situation. The within subject variability requires us to look at which subject you are, how different is your score in the absent condition from your mean, and how different is your score in the present condition from your mean. So we do that for each score in each condition for each subject, and we'd subtract off the mean for each subject. So in this case, this person is, below their mean in the absent condition and above their mean in the present condition. We'd square each of those deviations and then add them all together. And this tells us, after accounting for which person you are, how much variability is there in each of our scores. And in this case, our total within subjects variability is 5. And the total degrees of freedom here are going to be 8 for the 8 different participants that we have with 2 observations each. Next, we can calculate the total between subjects variability. One way you could do that, right, is to know, well, if we had a total of 23 and the within subjects variability was 5, then anything else must be the between subjects variability, and 23 minus 5 is 18. But the other way that we could do that a little bit more accurately is that we could actually calculate these sum of squared errors by taking the difference between each person's mean, because that's how your average, your typical score as a subject, relative to the grand mean, right? And if we look at how each person varies relative to the grand mean, that will tell us about the variability between subjects. So in this case, we're going to do that for each person, their mean minus the grand mean squared. we're going to take each of those deviations, but we have to multiply that by the number of observations that we have for each subject to make sure that this is getting weighted at the same level as the number of observations that we have over here. So we're multiplying that by 2 in this case, and we end up with 18. And we have 7 degrees of freedom because we have the 8 observations minus the 1 parameter that we're estimating in this situation to calculate this between subjects sum of squared errors. Next, it gets a little bit trickier because we're going to focus on explaining this within subject variance. So what we can do first is figure out the residual variance, how much error is left over and is not explained by the effective condition. And in this case, right, we're going to have 5 as our total within subject sum of squares, and we end up with 2.75 remaining. And the way we can calculate this, right, is we have the score for each person in each condition minus the average for that person. And then the next term is a little bit tricky, but we're going to subtract off the average deviance for that condition, right? So the other way that we could write this is you can think about we have the difference for each person in each condition minus the average difference in that condition, right? This person happened to be 0.5 points below their average. This person was 0 points below their average. This person was 1 point below their average. What we want to know is for each of those individual deviates, were they more or less different than the average difference in this condition? And what we would see is that in this condition, when the experimenter was absent, people generally tended to have negative scores. But they don't all have the same negative score. So there's going to be a little residual deviance there. Similarly, when the experimenter was present, people will all tend to have positive score differences, but they won't all have the same positive difference. So there'll be a little bit of residual deviance there. And if we sum all of those things together, we end up with 2.5 as the unexplained sums of squared errors. Next, we can then calculate what was actually explained. And again, one way we could do that is by recognizing that if our total within subject variance was 5 and we explained 2.75, well, that only leaves 2.25 left over, right? So 5 minus 2.75 is 2.25. But the other way that we could calculate that is much like we've done for the sum of squared errors explained by regression previously, where we'd look at the predicted value for each person relative to their mean minus the grand average difference that we would expect, right? So the other way that you can think about that is for each person in each condition, what is their predicted difference minus what was the grand average difference. And if we do those calculations, we take each of those deviates, square them, and then add them all together, we end up with 2.25 as the sum of squared errors explained by the effective condition. So you can see why actually removing this variability due to subjects is important up here, because our between subject variability is so much larger than the variability within subjects. If we had not correctly partitioned the variance into the different sources, this 18 sum of squared errors would be going into our error term. And then what we've explained based on our effect would look a lot smaller relative to the residual variance. But by correctly recognizing that we've crossed conditions with participants here, and we have 2 repeated measures per person, what that allows us to do is separate the variance into its between subject sources, right, reflected in what your average score is over here, and the within subject sources, reflected in the difference between these columns over here. And our condition effect actually explains a pretty large proportion of the within subject variance. And so by correctly treating these measures as repeated and running a repeated measures ANOVA, we're going to have a much more appropriate statistical test than if we had, incorrectly just run a factorial ANOVA here.